So this is question 6. For each of the circuits of figure 6, sketch the response of VO and IC to a 0 volt to 10 volt input pulse with a duration of 100 microseconds. You should assume that the diodes are ideal, i.e. 0 volt forward voltage drop, and take care to label your sketch with salient features such as time constants and aiming levels. In the case of figure 6b, you will need to work out the voltage reached by VO at the end of the pulse. In each case, write down the exponential form of the rising and falling edge responses and calculate the width of the output pulse, measured in figure 6a and figure 6c, at half its height, and measured in figure 6b, at figure 6a and figure 6c at half its height, and measured in figure 6b at 5 volts. In one of the three circuits, the output pulse height is not the same as the input pulse height. Right, so figure 6a is a circuit that looks like this. And our job is to determine what's going to happen when we put the pulse in. So we're going to have a graph of what the pulse will look like. This will be time, and this will be V in blue, and we'll have V out in green, and we'll have IC in red. So IC is going to be this current in the capacitor here. And B in is this voltage here. So we can draw our input because we know what it's going to look like. We'll have a pulse like that. And this is going to be our t equals a 0. And this is going to be t is equal to 100 microseconds. And the height of the pulse is 10 volts. Alright, so if we put 10 volts on here, and we assume that the capacitor has been discharged for a long time, so it's got no voltage across its plates at the moment, so V out is 0 in the beginning. The diode, so this point is 0. Let's assume we want to work out what the diode conduction state is. So we'll assume it's not conducting, take it out of the circuit and see what the voltage across it is. Well, at this end we've just managed plus 10 because we've just put this pulse in, 10 volts there. So that's at 10 volts. Now, I said this was discharged, so there's no voltage across there, and there's no current flowing because the diode's taken out at the moment because we're working out whether it's got a voltage across it that will switch it on. So if there's no current flowing in this branch, then there's no voltage across there either. So that's at 0. So this is at 0 and that's at 10. So it's reverse biased initially by minus 10 volts, and that would be the case for all the way along this pulse. So up until at least this point, all that stuff there, diode's not conducting. So we can ignore it up until this point here. So if the diode can be ignored, and we assume there's no current in the 220 ohm as well because the diode's switched off, so there won't be, we've really just got a first order RC circuit of 2K, and the capacitor value is 10 nanofarads for this one. I'm pretty sure. Yes. So in that case, well, we know that there's going to be an exponential shape for the voltage V out as the capacitor charges up through the resistor. So we can say, well, alright, if I had 10 volts here and no volts there, so it's completely discharged, so V out is 0, that means I've got 10 volts across the 2K resistor, so I can work out the current that flows around this loop. So I is going to be V upon R, which is 10 upon 2K, which is 5 milliamps. So that's the biggest current that there'll be, because as this current flows, it will be, the charge that it represents will be stored in this capacitor as an electric field, and the voltage across the plates will increase to support that electric field. So if we say some time later, an amount of time we don't know about, but some time later, this gets to say 4 volts, say. Well, that means we're still somewhere in this pulse period, and this is still 10. So we've got 4 volts there. That means this must have dropped to 6 volts. And if that's the case, you'd have a new current, I'll call it I prime, of V prime over R, which is 6 over 2, which is 3 milliamps. So the current's dropping, and we could carry on, so when this gets to 6 volts, this will be 4 volts, and it'll be 2 milliamps, or 2 milliamps, or whatever, and carry on in that fashion. But there really is no need, because we know what shape this circuit will give us in terms of the current and the voltage that's involved. It will be an exponential. So, as far as current goes, we'll have nothing, because nothing's happening, and the pulse will come on, and the capacitor will start to charge through the 2K resistor, and the peak current, which will occur on the edge, because that's where the biggest voltage is, because the capacitor is initially discharged, will have 5 milliamps. So we'll have a line just there, and thereafter, the fact that the capacitor is accumulating voltage, and this is fixed, will mean there's less voltage for the 2K, so the current will decrease exponentially. And it isn't necessarily going to perfectly fit into the pulse, but it might do. We will see. So we can find out something else. We can find out the time constant as well of this exponential. So we'd like to know what, sorry, not t. We'd like to know about tau, and tau is equal to R times C. So we've got 2 kiloohms and 10 nanofarads. So we have 2 times 10 raised to the 3 and 10 times 10 raised to the minus 9. Well, that's 2 raised to the 3, but this is the same as saying 1 times 10 to the minus 8. So I've got 8, 7, 6, 5. So I've actually got 2 times 1 is 2 times 10 raised to the minus 5 seconds. Well, that's the same as 20 microseconds. So I put a 0 in there and I'll drop that to a 6. So I've got a time constant of 20 microseconds. And I'll just clean out my intermediary lines so that we can see a bit more clearly. So I've got 20 microseconds here. What about the voltage? Well, as the capacitor charges up, the voltage across its plates acts to support the electric field that has to maintain that amount of charge. So the voltage will be charged, it will be rising exponentially as the current decreases exponentially. Somewhat like that. And it will rise up to 10 volts because the capacitor will fill up, essentially. I don't like the idea of it filling up, but you can think about it as filling up to the point where it can't be topped off anymore because it's reached the maximum that it can be filled to. and that will have a time constant of 20 microseconds as well. What happens thereafter? Well, at this point we essentially switch off the voltage source, and when we switch off the voltage source we can replace it by its internal resistance, which in this case is a short circuit because it's perfect, no internal resistance or anything. So we can just short out the voltage source, and now we've got an RC circuit in which the capacitor is the storage of energy in the circuit, and the 220 ohm and the 2K could potentially both be dissipators, and the diode is like a door with a spring. It doesn't actually dissipate any energy, it just determines if there's going to be current flowing in certain pathways or not. So will the diode be conducting? Well, we've got 10 volts here because we're at this point now. So assuming the diode isn't conducting, we'll have nothing across there because there's no current flowing. So that means we'd have 10 volts across there, which is more than 0, because this diode is perfect, remember. So that switches on at 0 volts with no internal resistance. So that 10 is more than 0, so yes, the diode will be conducting. So there'll be no volts across the diode, but there will be a current flowing, which means that we should have 10 volts across this resistor, because we've got 10 volts here and this is connected to that end. There's nothing here, so this resistor is in fact in parallel with the capacitor. Similarly, this resistor is in parallel with the capacitor as well, so we'll have 10 volts across that one as well. Sorry, that's a volt sign there. There we go. Alrighty, so the other important thing is now the capacitor is the store of energy in the circuit. It behaves like a source, which means that the current and voltage will face the same way. So IC actually has to be turned around. We need to make IC go that way. And an effect of this on our diagram is that whatever current we plot now will be negative to represent the fact that IC has changed direction. So we need to work out what the peak current is going to be by the same method as before. So we'll have I is equal to V upon R, where V is 10 volts and I is 2 kiloohms in parallel with 220 ohms. So what is that? Well, we've got 2E3 times 220 divided by 2E3 plus 220, 198.19 ohms. So we've got 10 over 198.2 ohms, which is 50.45 milliamps. 50.454, so it doesn't go up. 50.45 milliamps. Alright, so we know where the spike is going to come down to. The other thing we need to worry about is the time constant. So in the case of the circuit in its new configuration, the time constant will be tau is equal to the 10 nanofarads times parallel combination of the 2K and the 10K, which is 198.2 ohms. So I'm going to call it 200 because it will make everything a bit easier. So this is actually 2 times 10 raised to the 2, and this is 1 times 10 raised to the minus 8. So we'll have 876. So this is 2 times 10 raised minus 6 seconds, which is 2 microseconds. So we'll have we'll try and draw the lengths out sort of proportionally. So very swift decay, or drop to minus 50 something, followed by a pretty sharp exponential. So this will be minus 50.45 milliamps. Right, so what about the voltage? Well, the capacitor will be losing charge as it gives away its current to the circuit. So the stored charge in it will be falling. The electric field that's required to sustain that stored charge will increase as well, and as a consequence of that, the voltage that's across its plates will fall too. So we can expect an exponential decay like that. And we can write the time constant on as well. So this is tau is equal to 2 microseconds. Alright. So that's our sketch of what the pulse looks like and the output current and the output voltage. And we've got the peaks and everything. But the question then goes on to say, in each case, write down the exponential form of the rising and falling edge responses and calculate the width of the output measured in figure 6a and figure 6c. So we need to know what the width of the green line is between half the output height. So half the output height is at 5 volts because it's 10 volts is the peak output. So I know it's not quite in the middle, but to avoid interfering with the red current line, I'm going to call that 5 volts. It doesn't actually matter because the diagram is symbolic only. So we know that this distance here is 100 microseconds. And we know that there is an unknown amount of distance here. I call it T1. And there's another unknown amount of distance there. I call that T2. So what we've got to do is we've got to figure out how long between this point here and this point here. So we'll need to know what the exponential, the equations that describe the exponential shapes are, which is why the question asks us to write them down. So to do that, I'm going to rub out the circuit so I can write and have the graph at the same time. Alright, so we have to first of all work out T1. So the equation that describes the shape of this exponential is VR equals VA, which I'm going to call the aiming voltage, brackets 1 minus e to the minus t upon tau, where in this case t is T1. Or T will be T1. It's actually any T you like, but yeah, we'll leave it as T for now, and then we'll substitute it later. So, well, we know what V out's going to be because it's 5. We're interested in this point here. So we'll have 5 is equal to 10, which is the aiming voltage, brackets 1 minus e to the minus t upon tau, close brackets. So we're going to multiply out the brackets first of all. So we'll do 5 is equal to 10 minus 10 e to the minus t over tau, no brackets. I don't mind if you do it in less steps than this, but this is the sort of the simplest possible method of explanation is to write out every line, so I won't skip anything. So then we'll take the 10 across, so we'll do 5 minus 10 is minus 10 e to the minus t over tau. And then we'll divide through by the minus 10. So we'll have 5 minus 10 upon minus 10 is equal to e to the minus t upon tau. So then we'll take natural logarithms of both sides, so we'll have ln of 5 minus 10 over minus 10 is equal to minus t over tau. So we'll multiply through by tau, and we'll multiply both sides by minus 1. So we'll have minus tau ln 5 minus 10 upon minus 10 equals t. So if I insert tau now, for this equation, tau is 20 microseconds. So I can insert that and I can get an answer for t, and that will be t1. So we'll do minus 20 e minus 6 times logarithm of, open brackets, 5 minus 10, hang on, 2 sets of brackets required, 5 minus 10, close first bracket, divided by minus 10, close second bracket, equals 13.8629, but 3 microseconds. So 13.863 microseconds. So this is T1. So that period there is 13.863 microseconds. Alrighty, so we've got the first one, and then we need the second one as well. So we can, since I've written this up over there, I can get rid of it now. So we've got to do the same for T2, and this is a differently shaped exponential. Okay, it's exponentially shaped, but it's a slightly different exponential. For this one, VR is equal to VA e to the minus t over tau, where VA is the aiming voltage. And you can put 10 in there if you want to, because it's 10 that we're changing across. So we've got 5 equals 10 e to the minus t over tau. So we'll divide through by 10 to have 5 upon 10 is equal to e to the minus t upon tau, and then we'll take log, so we'll have the logarithm of 5 over 10 is equal to minus t over tau, so we'll multiply through by tau and multiply both sides by minus 1 to have minus tau is times the logarithm of 5 upon 10 is equal to t, and t is equal to, if we insert now the tau in this, sorry, it's not a very good tau, is it? Tau in this case is the 2 microseconds tau. So we've got minus 2e minus 6 times the logarithm of 5 upon 10 to the half equals, and it's 1.38629 microseconds, so 1.386 microseconds. Now, that shouldn't be at all surprising, because we divided the time constant by 10, and we've got the time gone down by the same order. So we've got 1.386 here. So our length of our output pulse width is going to be 100 plus T2 minus T1. So we've got 100 plus that bit less that bit to get from here to there. So we'll do 100 microseconds minus 13.863 microseconds plus 1.386 microseconds. And that will leave us with 100 minus 13.863 plus 1.386 87.52. So call it TP out. That's the output pulse width, or the length of the output pulse width is 87.523 microseconds, and that's what the question is asking for, and the answer that's given on the sheet is 87.53. So I must have, one of us, either my answer on the board or my answer on the sheet, has introduced a little rounding error, because if that was a 5 or more, that would go up to 3. It's probably in my exponentials, taking the logs and so forth, but the answer is correct anyway. So that's how you do 6 part A. So this is question 6, part B. And question 6 says, for each of the circuits in figure 6, sketch the response of VO and IC to a 0 to 10 volt input pulse with a duration of 100 microseconds. You should assume that the diodes are ideal, i.e. 0 volts forward voltage drop, and take care to label your sketch with the salient features, such as time constants and aiming levels. In the case of figure 6b, you will need to work out the voltage reached by VO at the end of the pulse. In each case, write down the exponential form of the rising and falling edge responses and calculate the width of the output pulse, measured in figure 6a and figure 6c, at half its height, and measured in figure 6b at 5 volts. In one of the 3 circuits, the output pulse height is not the same as the input pulse height. Right, well this is figure 6b, so we're going to have to heed the wisdom and make sure we do work out the output voltage height at the end of the pulse. But the circuit diagram looks like this. Right, and this is 10 nanofarads, this is 10k, and this is 4k7. This is D1, this is D2. Alrighty, so if the voltage source goes above 0, assuming that the 10 nanofarads is discharged to start with, if the voltage source goes above 0, then D2 will conduct, and if it goes below 0, D1 will conduct. And of course, whether D1 conducts and D2 conducts is actually dependent on the voltage on the capacitor as well. So if that changes, we'll have to be wary of what's going on. But as usual, we've got to draw a graph. And we'll have time, and we'll have V in blue and V out in green, and we'll have IC in red. And IC, I will choose positive values of IC to mean current flowing into the capacitor. And our input voltage is going to look like this. And this is 10 volts. Try and make that a bit bigger. 10 volts. And this is our T is equal to 0, and this is our T is equal to 100 microseconds. That's our pulse length. Alrighty, so what's going to happen? Well, when the pulse comes through, it will turn the diode on. The diode will have 0 volts across it because the diodes in this question are perfect. That's to say there is no 0.7. Anything more than 0 volts they turn on, and they turn on with 0 volts across them. So as soon as this edge goes into the circuit, the diode conducts and 0 volts across it, and then we've got the voltage across the 10k, and we're assuming that the capacitor's been discharged for a long time, so it's got 0 volts across it. So we've got 10 volts here, which is how we end up with 10 volts there, because there's 0 everywhere else. So if that's the case, we can work out the current in the resistor, and that will tell us what IC is. So we can have I is V over R, which is 10 upon 10k, which is 1 milliamp. That's 1 times 10 to the 1 divided by 1 times 10 to the 4 leaves you 1 times 10 to the minus 3. So we know already that there will be some current, there's nothing, and then the edge comes through and it goes up, and there's a current. I'll do it up a bit, and this is going to be 1 milliamp. And we know that as the capacitor voltage increases, because the current flowing into the capacitor produces the electric field, which is manifested as a voltage and a distance. It's volts per metre is the measurement of electric field. So we'll end up with a voltage across the plates, which is dependent on the distance between the plates and the dielectric coefficient of the capacitor. So there'll be this voltage, and it will be proportional to the amount of charge that's flowed into the capacitor with time. So we'll know it's going to go up a bit, but we don't really know how far. And we can say, well, what's the time constant? Well, the time constant for this one is going to be tau is equal to RC, which is 10 kiloohms times 10 nanofarads, which is 1 times 10 raised to the 4 times 1 times 10 raised to the minus 8. So that leaves us with 4 and 8, so this is 1 times 10 to the minus 4 seconds. And that is 100 microseconds. And we know that if you've got a circuit and you've got 5 time constants of not much going on after some event, then you will see the natural response of the circuit. We haven't got 5 time constants, we've only managed 1. So this green line probably actually a bit high. We could maybe do it even lower. Probably it's a bit more like that actually. So we're going to have to work out what this voltage is that it gets to, because that's going to determine what happens with the 4K7 resistor a bit later on. But we can also put in the current response, and it's going to look something like that. And we can put the time constant in as well. Okay, so what next? Well, we need to know what this voltage is before we can carry on. So we're going to have to use an equation. And the equation for this sort of exponential is V out is equal to VA, which is the aiming voltage, brackets 1 minus e to the minus t upon tau, close brackets. And the aiming voltage in this case is 10. Even though it doesn't make it there in the time we've given it, it's still 10, so we've got V out is equal to 10, 1 minus e to the minus t over tau, and we can substitute in for t and tau because we know that t is going to be 100 microseconds, and we know what tau is because we've already worked it out from the circuit. So we can multiply through by 10, and we can also sub in the numbers. So V out is equal to 10 minus 10, 10 minus 10 e raised to the minus 100 microseconds divided by 100 microseconds, all in big brackets, and then brackets around everything else. Oh, we don't actually need the outside brackets because I already multiplied through by 10, but anyway, we'll pop that into a calculator and see what comes out. So we've got, we'll do the exponential first. Could we agree that this is minus 1, the inner bracket, because it's 100 over 100 microseconds. So shift e raised to the minus 1, 0.3678, times 10, 3.678, 10 minus that, 6.321. So that's the voltage. VO at t is 100 microseconds is equal to 6.321 volts. Next digit's 2, so it doesn't go up. So we can put that on our diagram. We can 6.321. Okay, so now we know how far the capacitor voltage rose in the pulse period. We can figure out what's going to happen afterwards. So when the pulse goes away, obviously the pulse finishes. Sorry, the source can be removed and replaced with its internal impedance, which is a short circuit. And all these voltages disappear as well. And we know that the voltage on the capacitor at that point is 6.321 volts. So this is, sorry, I need a volt symbol there, don't I? Alrighty, so we can say, well, okay, this diode will conduct D1, because assuming it's not conducting, we'll have no current through this pathway, so the 4K7 will have no current through it, so all of those 6.321 volts will appear across D1, which is more than 0 volts, so D1 will conduct. So we'll have some current flowing out of the capacitor, so it's going to have to be negative because we've got current in as considered positive, so current out must be considered negative. So we'll have some current, and the maximum value of that current will be the voltage, the maximum voltage on the capacitor divided by the resistor, and in this case it's the 4K7. So we've got I is V upon R, which is 6.321, divided by 4K7, which is about 1.2 milliamps by the looks of things. 6.321 divided by 4.7E3, 1.344 milliamps. 1.345 actually. So it's 1.345 milliamps, and that's the peak current that it'll get to. So we can have something like this. And there'll be a decay here. And this decay will be, so we can write that on. Wow, really missed that, didn't I? Never mind. 1.345 milliamps. And this time constant we know about as well. It will be the 4K7 and the 100 nanofarads. So we'll have a time constant here of, well, it's 10 nanofarads times 4.7 kiloohms. So that's 1 times 10 raised minus 8 times 4.7 times 10 raised 3. So that's 8765. So we've got 4.7 times 10 raised minus 5, which is 47 microseconds. So I'll get rid of the intermediary lines and we can just have the 47 microseconds. And the voltage that will result is the capacitor is discharging, so the 6.321 that we've got will decay away. But we can see that 47 microseconds is still, you're only getting 2 time constants in this period, so it's going quite a long way off the right hand edge of the graph before we get back to anything normal. So the other thing we need to calculate is the time that's involved in this pulse, and the question says up to 5 volts is where we need to know about. So, well, that's 6.3, so 5 is probably going to be around here somewhere. So this we'll call that 5 volts, and this will be our T1, and this is our unknown distance. That distance there. And there'll be another distance as well, which is this one here, and we'll call that T2. So we need to know what they are. And we can apply the same equations that we've applied in 6 part A. We know that the equation for this sort of exponential is VR is equal to VA 1 minus e to the minus t upon tau. And we know that at 100 microseconds it gets to 6 volts, so it shouldn't be too difficult for us to work out what the time involved is. We'll do the same maths that we usually do, where this is 5 is equal to 10, 1 minus e to the minus t upon tau. And this is, the reason it's 10 is it's not aiming for this point, it's aiming for 10. Somewhere way up here in time, at 500 microseconds or so, we will eventually get to 10 volts. But it's aiming for 10, even though it never gets there. So we'll do multiply through by the 10, give 5 is equal to 10 minus 10 e raised to the minus t upon tau. Take this, subtract 10 from both sides to leave 5 minus 10 is equal to 10 e to the minus t upon tau. And then we'll divide through by 10 to have 5 minus 10 over 10 is equal to minus t over tau. We'll take logs of both sides. Oh, sorry, I missed an e, didn't I? Yeah, so we'll take logs, and that leaves us with minus t over tau. And then we'll multiply through by tau, which will give us tau ln 5 minus 10 over 10 is minus t. And then we'll multiply both sides by minus 1, which leaves us with minus tau ln 5 minus 10 over 10 is t. And that's actually one of the same equations that we had in question 6, part A. So the tau in this case is the 100 microseconds. So we've got minus 100 e minus 6 times ln, open bracket, 5 minus 10, close bracket, divided by, oh, I made a mistake there, didn't I? No, there's a minus sign that I never dealt with. Minus 10, naughty. Minus 10 is 69.31 microseconds. 315 microseconds. If I hadn't seen that when I did, it wouldn't have made a big deal, because if you try and do ln of something that's negative, your calculator goes, I can't. So I would have figured it out pretty quickly anyway, and so would you have in an exam. So we know that this T1, which I'll move, T1 is 69.315 microseconds. And we need to know about T2 as well. And just like in question 6 part A, we've got an equation for this exponential too, and that's going to be V out is equal to VA e to the minus t upon tau. And VA in this situation is 6.321 because this is the point that this voltage is decaying from. So we got, and it's decaying down towards 5 volts. So we've got 5 is equal, it's decaying towards 0, but the interesting point is when it gets to 5. So 5 is equal to 6.321 e raised to the minus t upon tau. So we'll divide both sides by 6.321 to yield 5 upon 6.321 is equal to, e raised to the minus t upon tau. So if we take logs of both sides, we'll get ln of that is minus t over tau. So if we multiply both sides by tau, we'll get tau there and that tau will go away. And then we'll multiply both sides by minus 1 and get rid of the minus sign. So this tau is the 47 microseconds. So we've got minus 47 e minus 6 times logarithm of brackets 5 over 6.321 close brackets is, and it's 11.0187 microseconds. So that's T2, which is this one here. So it's actually I'll just write T2 there and be done with it. So to work out the total pulse width, output pulse width, we've got 100 minus 69.315 from the time it takes to get to 5 volts plus 11.0187 the time it takes to drop to 5 volts after the input pulse is finished. And that is 100 minus 69.315 plus 11.0187, 41.7037 microseconds. And that is pretty much the same as what's on the sheet, which is 41.7. So that's how you tackle this question. And these questions in question 6 are all broadly the same thing. You've got to figure out what has to happen to make the diodes conduct, to find out what the exponentials are going to look like, and work out what the time constants will be, and then you just apply the exponential equations for RC circuits to get the lengths of time or voltages that the questions are asking for. This is question 6 part C, and the question says, for each of the circuits of figure 6, sketch the response of VO and IC to a 0 volt to 10 volt input pulse with a duration of 100 microseconds. You should assume the diodes are ideal, i.e. 0 volts forward voltage drop, and take care to label your sketch with salient features such as time constants and aiming levels. In the case of figure 6b, you will need to work out the voltage reached by VO at the end of the pulse. In each case, write down the exponential form of the rising and falling edge responses and calculate the width of the output pulse measured in figure 6a and figure 6c at half its height and measured in figure 6b at 5 volts. Note, in one of the 3 circuits, the output pulse height is not the same as the input pulse height. Right, so figure 6c, which is the one we're on now, looks like this. We've got some output and the resistor in parallel with the output, and in parallel with that a capacitor. And off the top of the capacitor we've got a diode in series with a resistor, and then we have the voltage source. Alrighty, and this is R1, and this is R2, and this is C, and this is D, and R1 is 2K, and R2 is 3K, and C is 10 nanofarads. And we'll draw IC as flowing into the capacitor. So we have to decide what is conduction for the diode, what state or what situation of the circuit will give us conduction in the diode. We'll have to sketch a graph of what's going to happen in terms of voltages and currents. So we'll have V in blue, which will look like this, and this will be T equals 0, and this will be T equals 100 microseconds. And we'll have V out in green, and we'll have IC in red. And the input pulse height is 10 volts. So if you've been working your way through the sheet, hopefully you're really getting the hang of these by now, and you'll be able to see fairly swiftly, I hope, that the diode will conduct as soon as the rising edge of the pulse passes into the circuit. And we can do some calculations to work out what the current is going to be. Now, there is this potential divider between R1 and R2, which will adjust the ending voltage for the pulse. But in the situation where we've just switched the circuit on and the pulse has come in, this capacitor is discharged, so it has no voltage across it. As a consequence of that, at the instant the leading edge of the pulse enters the circuit, there is all of the 10 volts across the 2 kΩ resistor. Because this voltage cannot change instantly. If it was just a potential divider, yeah, you'd get 10 shared in the ratio of 3 to 2. But because this capacitor needs to charge up, because the capacitor and resistor are in parallel with each other, so this cannot get a share of this voltage unless this capacitor is charged up to whatever that share is. So as soon as the pulse comes into the circuit, IC, or rather I in the resistor as IR1 will be VI divided by 2K, which is 10 over 2K, which is 5 milliamps. So there will be a rising exponential in voltage, and therefore there will be our usual current shape, which is like that, and this will decay away. But we don't know how fast, but we do know that that's going to be 5 milliamps. To work out the time constant and be able to draw what the circuit's up to, we'll need to know the time constant. Now, for this situation, it's actually quite, it's not obvious what's going on, but tau is actually C times the parallel combination of R1 and R2. So this is 10 nanofarads times 2K times 3K over 2K plus 3K, and that is 2 times 3 over 2 plus 3, 1.2 times 10 minus 9, it's 12 nanoseconds, sorry that's microseconds, 12 microseconds So I did all these in individual, not in kilo. I did it as 2 and 3 as opposed to 2K and 3K. So it's 12 microseconds. So if we've got 100 microseconds in the pulse, well, 5 12s is 60. So by 60 microseconds in, we ought to be in a situation where we've observed the whole natural response of the circuit. So for our current, 60 is probably about there-ish, I would have thought, maybe a little bit to the left. So we're looking at something like that, or thereabouts. And for voltage, we've got to be careful there, because ultimately this potential divider will take effect, and we will end up with V out is equal to V in times R3 over R2 plus R3. So this is going to be 10 times 3 over 2 plus 3, which is 10 3 to 30, divided by 5 is 6 volts. Yeah, 5 6 of 30, so 6 volts. So we know that we're aiming for somewhere around here, and it's going to happen sort of by this point, so something like that. And this current one, of course, it doesn't stop there, it's just 0. And we can label this as 6 volts. So what about the discharge? Well, when this the trailing edge of the pulse, or when the pulse finishes, this diode will be reverse biased, because the voltage on the capacitor will now be 6 volts, and the voltage here will be 0, because we'll be able to remove this source, which is essentially switched off, so we can replace it with its internal impedance, which is nothing, so a short circuit. And then the diode's reverse bias, the 2K has nothing to do with anything. IC is changing direction. The current's now leaving the capacitor, which is the energy storage for the circuit. And there is a circulating current around there, around between the capacitor and resistor, and the capacitor is discharged. So we have some current in the R2, but nothing in R1. So what can we say that current is? Well, we can do IR2 is 6 upon 3 milliamps, which is 2 milliamps. And strictly speaking, it's minus 2 milliamps because we changed the direction of the sign. So if that's 5 milliamps, 2 milliamps probably is about there. And there'll be a new time constant as well. And the time constant is now 10 nanofarads in parallel with 3 kiloohms. So our new time constant, we'll call this tau 1, call this tau 2, will be 10 nanofarads times 3 kiloohms, which is so some 1 times 10 to the minus 8 times 3 times 10 to the 3, 8765. So that's 5 times 10 to the, 3 times 10 raised minus 5, which is 30 microseconds. So we have time constant for this bit is 12 microseconds, and a time constant for this bit is 30 microseconds. It's quite a bit longer actually. And similarly, the voltage will decay back towards 0 as well. So we can draw on the time constant there. Right, so now we've got the response of the circuit figured out. we need to be able to calculate what the pulse width is at the output, and it says half the height of the input signal. Well, in this case that's 3 volts. So as with the prior problems, there are 3 times involved. There's this time here, T1, which is that time. There's the 100 microseconds, and there's the T2, which is this time here. And we'll have to work those out. So, oh, I didn't actually label my graph properly, did I? Tut tut tut. Missed that one. It's -2 milliamps. So I'm going to rub out the stuff on the bottom, the calculations, so that we can work out the times. So for the rising exponential, we've got VR is VA 1 minus e to the minus t upon tau, and in this situation VA is 6 volts. It's the actual aiming voltage is 6 volts. So we have not 10 as it has been in the past. So we're after 3 volts is equal to, that's half of 6, is 6, 1 minus e to the minus t upon tau, and we'll multiply through by 6 to give 3 is 6 minus 6 e to the minus t upon tau. We'll take the 6 across, or subtract 6 from both sides, which will give us 3 minus 6, and we'll divide through by minus 6 as well, is equal to e to the minus t upon tau. And then we'll take logs of both sides, which will give us ln of 3 minus 6 upon minus 6 is minus t upon tau. Then we'll multiply both sides by tau to give us that lot's minus t, and then we'll multiply both sides by minus 1, and we'll just have t is that lot. And tau in this case is the 12 microseconds. So in that case we'll have minus 12e minus 6 times open brackets, oh no, sorry, times the logarithm of open brackets, 3 minus 6, close first brackets, divided by minus 6, close second brackets, is 8.3177 microseconds. So that's this time here is 8.3177 microseconds. Then for T2, we've got the other equation for this exponential, or the equation for this exponential rather than this one, which is V out is equal to VA e to the minus t upon tau. And we'll sub in the numbers, and of course this is 3 is equal to 6 e to the minus t over tau, and tau is 30 microseconds this time. So we'll divide through by 6, so we'll end up with 3 upon 6, and the ln of that is equal to minus t upon tau, multiply through by tau, and then multiply through by minus 1 to yield t is equal to, well, actually didn't write 3 down there, did I? It's 3. So we've got minus 30 microseconds times logarithm of a half is 20.794 microseconds. Alright, so now we can do our usual thing where this is T1 by the way, and this is T2. So we'll do 100 minus T1, which is 8.3177, plus 20.794. I'd be really worried if this was smaller than that, because this one's got the longer time constant. And obviously it doesn't make sense otherwise. So 100 minus 8.3177 plus 20.794 is 112.4763. microseconds. So the output pulse length is longer than the input pulse length. Entirely possible. And the answer on the sheet is 112.5. So that's consistent. And that's how you do question 6 part C.